Good evening to all of you. Hello, I am Saikat Giri, your chemistry educator. Today we are going to discuss about one of the most important topic, you can say confusing topic in chemistry, where many students feel doubtful that how it happens, why it exists, how it works, that is back bonding. So today we are going to discuss about back bonding. Let's discuss it properly, and elaborated description you will get in my lecture. So be with me. Let's start. What is back bonding? The first logic of back bonding is, see, it is written already bonding means bond is already present. So back bonding mane we can say that back bonding means bonding is made once again. If bonding is made once again, we consider it as back bonding. You can consider as definition of back bonding is this. So, which type of compounds are there or which type of orbitals are there that are going to make back bonding? Let's see. Before knowing back bonding, we need to know about coordinate bonds. So, what is a coordinate bond? Let's understand. One orbital that is completely filled, another orbital that is vacant. So what we need? We need a filled orbital and a vacant orbital we need. We need a vacant orbital. This filled orbital will donate its lone pair to its vacant orbital via coordinate bond. Then there is a chance of back bonding. So what is a coordinate bond? When a bond is made in between vacant and filled orbital and both are sharing the electron, in that case coordinate bond is formed. And we know the concept of covalent bond as well. In case of covalent bond, what happens? We have taken two orbital. This is half filled, this is also half filled. According to Pauli's exclusion principle, no two electrons have same spin, so both are in opposite direction. So we are taking half filled orbitals. When half filled orbitals, this is also half filled. We have taken two half filled orbitals. We represent them like this. This is one half filled orbital. Another half filled orbital is sharing. So in this case, bond is formed. Here, covalent bond is formed. In case of coordinate bond, one filled orbital, this is completely filled. One is completely vacant orbital. It is also sharing its electron. In that case, coordinate bond is formed. Here, coordinate bond is formed. So, how can we explain back bonding then? In case of back bonding, we consider the concept that this bond we can consider as pi dative bond. What is dative bond? Dative bond is nothing but a coordinate bond. This back bonding happens because of unequal sharing. Obviously it is an unequal sharing. How can I say it is an unequal sharing? Because one has no electron and one's orbital is completely filled. That's why I am saying that by unequal sharing, whose unequal sharing? Unequal sharing of pi dative bond, then back bond is formed. So back bond formed by unequal sharing. This type of bond, regarding back bond we are talking about, this type of bond is formed within a molecule by intramolecular acid-base reaction. So this type of bond are formed by intramolecular acid base reaction. So by intramolecular acid base reaction, back bonding is formed. How many types are there? Why bond is made once again? Let's check all the details. So what are the conditions of back bonding? First we need to know about them. Let's check. And what are the varieties of back bonding? We can say there are basically three types of back bonding. What are they? The three types of back bonding we can consider. The types of back bonding. So, what are the types? First type I can say it is considered as p-pi back bonding. That is p-pi back bonding. In which case we can see? In case of second period element we can see this. p-pi back bonding. Hybridization is generally sp, sp2 or sp3. sp or sp2 in general case. sp3 generally does not undergo back bonding. Why? Because for back bonding molecule need to be in the plane. We know sp2 hybridization means trigonal planar geometry. So if it is trigonal planar geometry, in that case it is on the plane. Now if it is sp3, it is tetrahedral. So tetrahedral structure or pyramidal structure, it is out of the plane. So it is impossible for them to form back bonding. Second type is considered as p-pi d-pi back bonding. This part is most asked in exams. p-pi d-pi back bonding. It happens in between second and third period elements. And third type is considered as d-pi back bonding. d-pi back bonding. And it happens mainly in third period element. General hybridization can be shown as sp3d, sp3d2 or sp3d3. In this case also we generally see sp, sp2, these type of hybridization also observed. So there are basically three type of back bondings: p-pi p-pi, p-pi d-pi and d-pi d-pi back bonding. Now what are the conditions of back bonding? When back bonding is formed in a molecule? Let's check that. So the conditions of back bonding, the first condition we can take, let's erase this. Conditions of back bonding we are going to discuss. So first point we can say we are discussing conditions of back bonding. What are the conditions of back bonding? First point you can say one atom should have vacant orbital and another atom should have filled orbital. So first point you can say one vacant orbital and one filled orbital. So first requirement is one vacant orbital, another filled orbital. What is the second requirement? One atom should be of second period and another atom should be of third period, because we know it is observed in between second and third period. So it is observed in between second period elements and third period elements, not in any other element. So we can say that it can be observed in second and third period elements. So requirement is second and third period elements. So if the elements are in second period or in third period, then it is observed. Back bonding is being observed. Let's take few questions and discuss. It will show back bonding or not. Let's take the questions one by one. So I am taking few questions that is asked in previous IIT, JEE and mains exams. First I am taking BeF2. In case of BeF2, will it show back bonding? Let's check out. In case of Be, beryllium, we know that it is a second period element. In case of fluorine, fluorine is present in which period? Fluorine is also present in second period element. So both are second period elements. Does fluorine has lone pair? Does Be has vacant orbital? Yes. Be is not filled and it has vacancy of electrons. How can I know that it has vacancy of electrons? BeF2. F2 means two bonds are formed. Each bond has two electrons. Two bond has four electrons. So in case of BeF2, we can say that there is lone pair present. So it is a second period element. Lone pair present mane it is a filled orbital. So in this case, back bonding will be observed. Let's take few more questions. You try to solve by yourself. If you can't, I'll solve. Second case we are taking BH3. We can take another case of BF3 we can take. Will it show back bonding or not? Take another case, very famous, BCH3 whole 3. Another case I am taking for AlCl3 and SiF4. Let's check one by one. In case of BH3, let's check out. This is second period. Hydrogen is first period element. There is no chance of back bonding. In the next case, BF3, B is second period and F3, fluorine. Fluorine is a second period element. It has also lone pair present. So this will show back bonding. This shows back bonding. BCH3 whole 3. In case of BCH3 whole 3, what is going to happen? You can check. There is no lone pair in this molecule. You can connect like this. BCH3 whole 3 like this. There is no lone pair present here. So there is no chance of back bonding. We take AlCl3. AlCl3 in this case, it is a third period element. Both are third period element. So both are third period element. Then there is a chance of back bonding. In case of SiF4, what is the criteria? See, in SiF4, it is completely filled. It is completely filled. But in this case, two lone pairs are also there. Silicon, atomic number 14. Is there any lone pair present? Silicon does not have any lone pair. It has vacant orbital. But fluorines, they have lone pair atoms. Though its octet is filled up, it has a lone pair, so there is a chance of back bonding. Yes, SiF4 will show back bonding. Don't consider like that octet is not filled up, so back bonding will happen. There is no logic like that. If any element has vacant d orbital, it has vacant d orbital, then there is a chance of back bonding if another element is having lone pair. Now, how can you understand any element having vacant d? There is a simple trick that I follow to solve, that is d block elements, or better to say like vacant d. Vacant d. Which of the following compound has vacant d? A simple logic. Atomic number 13 or more, they have vacant d orbital. Just remember this. You can understand that element has vacant d orbital or not. So if it has vacant d orbital, if their atomic number is 13 or more. So this is the basic logic for solving the questions for back bonding. How to calculate p pi, p pi and p pi d pi? Let us consider I am taking one molecule, that is SO3. Generally this example is a very famous example. We will discuss elaborately what is happening in this compound. See, for SO3 sulfur, what is its atomic number? Sulfur is 16. So 1s2, 2s2, 2p6, 10 done. 3s2, 12, 3p4. So the configuration is like this. We are taking only the valence orbitals. So I am taking 3s, 3s2, 3s2 and 3p4. 1, 2, 3 and 4. 3s2, 3p4. This is ground state for sulfur. In this case, vacant d orbital is present. Here, vacant d orbital is present. I told you how to decide any element has vacant d or not, atomic number 13 or more, then it has vacant d orbital. So, in ground state, this is 3s, this is 3p, and we are considering this is 3d orbital. In excited state, what is going to happen? This one electron will jump, but generally in excited state it happens that electron jumps. Here are two electrons that are fielded, so these electrons will jump to d orbital. So in case of excited state, arrangement will be like this: 3s and this is 3p. In 3d orbital, two electron jumps. One jumps here to here, another jumps here to here. So another two electron that is jumping to 3d orbital. So in this case, when SO3 is made, you can see the structure of SO3: S double bond O, double bond O, double bond O. So in each case, there is 1 sigma and 1 pi with each SO. Whenever bond is formed, first sigma bond is formed. After formation of sigma bond, pi bond forms. So first the electrons that are available, that will make sigma bond. After that, it will be involved in making pi bond. Let us take oxygen molecule. In case of oxygen, what is the general configuration? Oxygen atomic number is 8. So we can take 1s2, 2s2, 2p4. We are taking the outermost subshells only here. And here for p orbital, what is going to happen? 2s2, this is 2s, and in this case 1, 2, 3 and 4. You can check, for each oxygen there are two unpaired electrons for each oxygen. And in case of, let us show it by another color for oxygen, so that when we mix up the elements, it will be easier for you to understand that which electron is jumping in which place. So this is 2p and 2s electrons arrangement. Now you can check here 3 orbital and 1 4 means 1 3s and 3 3p orbitals are having 1 electron each. 3d also having 1 electron. We'll talk about d later. Now for each oxygen you can check there is 1 electron available. So for pairing, what is the requirement for this atom? This sulfur atom, it will take 1 electron from oxygen. You can check for each sulfur. For sulfur 1, 2, 3 oxygen available, and the number of bonds connected with each sulfur, that is 2. So 1 sigma 1 pi bond, and it is connected. While forming sigma bond, we need electrons. First sigma bond is formed. Let us consider SO3. First this is formed. After that double bond starts. So first sigma bond is formed. We will first check with sigma bond. Let's see. In this case, 1 electron, this 1 electron comes here. This is 1 oxygen involvement with S and S. Now see, S and p orbital we have. What will be the its hybridization? 1 S involved. Now 1 more available. 1 p involved. How many oxygen you have taken? 3. 1 more. So see, for oxygen, total 3 oxygen, 6 electron available. 1, 1, 2. So for 1 oxygen you can check 2 electrons are there, 2 unpaired electrons are there. So for 3 oxygen, 2, 2 and 2, total 6 electrons are there. Among these 6, for making this single bond, 1, 1 and 1, total 3 electrons are involved first. So you can arrange these orbitals in such a way. For sulfur, the arrangement is becoming this 2, 2 and 2. We can check 1 S and 2 P are involved. So O, O and here also O connected. Hybridization is sp2. We can check. Now, how many electrons left? Oxygen have rest 3 electrons left. These all are S and P electron. Now check. This is remaining unpaired. This is unpaired. This is also unpaired. Total 3 unpaired electrons are left. And here from 6 electron, 3 electron is used. So left electrons are 3. So 1 electron will come from oxygen and make 1 bond here. That is your p orbitals bond. So you can say 3 bonds are made and single bonds are made. Now it is the time to form pi bonds. So by this electron, 1 pi bond is formed. 1 bond, 2 electron. Previously 1 electron of sulfur was there, 1 electron of oxygen came. So now it forms 1 pi bond. Another case, another electron come, 2 electron used, rest 2, another electron come. Now you can see over here, here is p pi, and this is p and d involved. This becomes oxygen's p, sulfur's d. Here oxygen's p, sulfur's p. It makes p pi. Here oxygen's p, sulfur's d. So this is p pi d pi. How many? 2. So 2 p pi d pi bonds are formed. So whenever you are taking SO3 molecule, in SO3 molecule there are, for SO3 I can say, in this case S double bond O and double bond O, we can say that in this case 1 p pi and 2 p pi d pi bonds are present. So this is the basic logic to understand how many p pi, how many p pi d pi back bonding possible in a compound. These are a few questions I have taken from many previous year exams. How to count p pi and p pi d pi bonds. That is our logic. So what are the trick to solve these type of questions? First trick that I use, first trick is find hybridization. Find hybridization, and hybridization should be sp, sp2, sp3, sp3d, etc. If there is no hybridization, then it cannot be found out. For example, any molecule we are taking pH3, it has no hybridization. Why it has no hybridization? Try to find out. If you couldn't solve, ask me in the comment box or in my next lecture. I'll answer you. Why pH3 does not show any hybridization? In this case, find hybridization. It should be sp, sp2, sp3 or sp3d. Means elements should have hybridization. Then we can say that, okay, it can show p pi or p pi d pi. This is the first logic. Second, if it is a second period element, if you are taking second period element, for second period element, only p pi back bonding is observed. For second and third, p pi d pi is observed. Why? Because in second period, there is no point of d orbital. So from third period, p pi d pi back bonding is possible, because if atomic number crosses 13 or more, means atomic number is 13 or more, in that case only p pi d pi back bonding can be observed. Let's take the questions one by one and we'll find out how many p pi or p pi d pi back bonding is there. Let's take the first question. First question is your NO3 minus. How to draw? N double bond O, single bond O minus, single bond O minus. See, nitrogen and oxygen, Both are second period element. So here only one p pi back bonding. Second case is NO2 minus N double bond O single bond O minus NO2 minus. In that case 1 2 3 one lone pair will be there. So in that case 1 p pi back bonding. Next case we take COCl2 C double bond O Cl. In this case also both are second period element. Here is one p pi back bonding is observed. In case of PO4 3 minus, we can check P double bond O single bond O minus single bond O minus single bond O minus. See, atomic number of phosphorus is 15, so it is 13 or more in that category. So this bond is oxygen's P and phosphorus D. So p pi d pi back bonding. In case of SOCl2, let us think. SOCl2, sulfur double bond oxygen connected with another two chlorine atoms. Now in this case you can find out here sulfur is 16. So in this case there is p pi d pi back bonding. Sulfur's back end D, and in case of oxygen P. So p pi d pi. So first series we have solved NO3, NO2, COCl2, PO4 3 minus SOCl2. For SO2Cl2, what will be the arrangement? Let's see. When we are checking for SO2Cl2, I am erasing this part. So we are finding out for SO2Cl2. Try until I erase. You try to solve. In case of SO2Cl2, let's check. When you are taking SO2Cl2, that is your question number 6. So sulfur double bond oxygen, 2 chlorine. So in this case, this one and this one, total 2 p pi d pi back bonding is possible. In case of ClO4 minus, 7th one, ClO4 minus, chlorine O4, so double bond O, valency 6, and this one 7, ClO4 minus. Chlorine has vacant d orbital, so 1 2 3, total 3 p pi d pi back bonding is possible for ClO4 minus. Let us take ClO3 minus. In case of ClO3 minus, double bond O, single bond O minus, one lone pair will come. So in this case, what will happen? 1 and 2. So there 2 p pi d pi back bonding is there. When pi bond is there, I am checking always double bond, because pi bond is only present in double bond system. In these cases, ClO3 done. XeO4, question number 9, that is XeO4, xenon. It is a noble gas. In this case, helium, neon, argon, krypton, xenon, radon. These are the noble gases. Atomic numbers are helium 2, 10, 18, 36, 54 and 86. These are the respective atomic numbers. So in case of xenon, it is 54. Let's check for this. XeO4. So double bond O, valency 8 filled up. Here 4 p pi d pi back bonding. In case of XeO2F2, let's check question number. Let's erase this first. So in this case, XeO2F2. Whenever you are solving, take a pause, then start solving the question, then check with my answers. XeO2F2, Xe double bond O, and 2 fluorines are connected. 1, 2, 3, 4, 5, 6. One lone pair is there. In this case, 2 p pi d pi back bonding, XeO2F2. XeO3, in case of XeO3, arrangement is Xe double bond O, double bond O, double bond O. This is XeO3. In case of XeO3, there is 3 p pi d pi back bonding. So this is all about your p pi d pi back bonding. In these cases, how many p pi d pi back bonding is possible in the compound? There is one more logic regarding p pi d pi back bonding. What happens in a molecule when p pi d pi bonding is observed? How can we answer that type of questions? Let's take one question depending on that topic. So, we are going to take one question depending on that topic, that what will happen with bond order, what will happen with bond length whenever p pi d pi back bonding is happening, or is there any change in the hybridization of the molecule? Is there any change in their acidic strength? Their basic strength remains same or changes? We'll check with respect to some questions. Now we'll discuss about how acidic strength, basic strength, bond length and bond order is affected by back bonding and how shape of the molecule changes. Let's check. For example, I have taken NCH3 whole 3 and NSiH3 whole 3. In both the molecules, we have to compare their acidic strength, their basic strength and their hybridization. Planar character or non-planar character means what is the symmetry of the element. We'll check that. Before going further discussing this question, let me tell you one more thing before discussing this. Lewis acidic strength is proportional to 1 by back bonding. What is Lewis acidic strength? What is the Lewis acid? Any substance that is capable of taking lone pair, that is the Lewis acid. If we compare in case of BX3 molecules, boron trihalides molecules, let us consider BF3, BCl3, BBr3 and Bi3. In these cases, if we check the order of Lewis acidic strength, Bi3 have highest Lewis acidic strength. As a result, the chances of back bonding will be highest in BF3, then BCl3, then BBr3, then Bi3. So highest back bonding chance will be here. So acidic basic strength is also affected by back bonding. Let's take the first question. In this question, we are going to discuss question number 1. That in case of NCH3 whole 3 and NSiH3 whole 3, which is having planar geometry, first we'll discuss that. Let's check out. After that, we will go to the next part of the question. See, NCH3 whole 3. So, N connected with CH3, another CH3, there is one lone pair. We know to find out the hybridization, number of sigma bond plus number of lone pairs. So 3 plus 1, total 4, hybridization is sp3. sp3 has general geometry tetrahedral, but in this case, this lone pair is present, no separate atom is present, hybridization will be pyramidal. We can say this is trigonal pyramidal. Its shape is trigonal pyramidal. Geometry is tetrahedral only, but shape changes wherever lone pair comes. Now, if we take for NSiH3 whole 3, NSiH3 whole 3, we know in case of silicon, it has vacant d orbital present. So silicon has vacant d orbital. So it has a place to accommodate this lone pair. So nitrogen is going to make back bonding with SiH3. So here back bonding happens. In this case we can say back bonding happens. But in this case no back bonding, no chance of back bonding. Because carbon do not have any vacant orbital to accept the lone pair from nitrogen. But in this case there is a chance of back bonding, and here back bonding happens. So as back bonding happens, this lone pair will be used and this compound will transfer its shape to this. So this becomes trigonal planar. So this is a planar molecule, where it is a non-planar molecule. This is pyramidal molecule. Let's talk about the basic strength of the molecule. Its lone pair is already used in back bonding. So what we can say about their basic strength? Basic strength. What we can comment about basic strength? We can say that lone pair is used in the second case. This is I am marking at second case, this is first case. So as lone pair is used in the second case, it does not have any lone pair to donate. As a result, it is a bad Lewis base. In this case, it has lone pair unused. As lone pair is unused, we can say regarding basic strength, 1 is a better base than 2. So you have seen back bonding, how it affects the planarity of the molecule, how it affects the basic strength of the molecule. Another concept we will take regarding bond length and bond order of a molecule. Let's take one more question and we will conclude today's lecture. So one more question we are going to take. For example, I am taking BH2N SiH3 whole 2. BH2N SiH3 whole 2. This is my first part. Another case I am taking BH2N CH3. My question is, in which of the case bond length is longer and what is bond order for this molecule for BN bond length? We have to compare BN bond length and bond order. How to compare? Let's check out. We know that this nitrogen has lone pair. For this nitrogen, it also has lone pair. You see, nitrogen has the capacity to donate its lone pair, and B has vacancy of electrons. Nitrogen can donate its lone pair to B. Here also it can donate its lone pair to B. In this case, there is only one option, that is B. It can only donate its lone pair to B. But in this case, silicon has vacant D, another silicon has vacant D orbital. It has 1 chance, 2 chance, another one 3 chance. So it has 3 chances to make bond and 3 chances to share its lone pair. So this nitrogen is confused with whom it is going to make back bonding. As a result, back bonding is better in this case. Back bonding, we can say that Here back bonding is more effective as it has only one chance to make back bonding with B. If back bonding is more effective, what can we comment? You see, back bonding is happening in the molecule. So, in this case, bond order will increase if we mark it as 2. For back bonding, bond order is greater in 2 than 1. As a result, bond order and bond length are inversely proportional to each other. So, bond length will be greater in the first case in comparison to the second case. That's all for today's discussion. Thank you everyone. I hope you like my lectures. If you have any confusion in any other topic, please feel free to comment in the text box. I like to explain another topics as well. If you have confusion, my motive is always helping my students and whoever is coming for gaining knowledge. I am learning and I also help people to learn. So like and subscribe and be connected with me. Thank you everyone.